molecular dynamics as it was described yesterday, so in Bohr-Oppenheimer form. Then I'll make a little digression on constrained molecular dynamics. And that's just a classical molecular dynamics question. You've done, in the lab yesterday, you've done a little simulation with constraints. And I will discuss a little bit more in detail how this is made, how this is implemented. And that, in turn, will also help us understand Parrinello molecular dynamics, because there's a concept there that's related to constraints that is used in the Parrinello. So then I'll discuss a little bit more about the practical problems you have if you want to try to implement these methods on parallel computers. And finally, a little bit examples of application. So again, this is going to be a bit technical, so please interrupt me anytime if you have any question or if something's not clear on the slide. All right, so just to remind you of what we're talking about here, we're going to have to solve the Kohn-Sham equations of density functional theory at each step of our molecular dynamics simulation. So this is just the basic facts about the Kohn-Sham equations, one solution for molecular orbital. There are in general the complex scalar functions in the domain that we have, and usually we have a periodically repeated cell. And they're coupled, all these differential equations are coupled since all the molecular orbitals are basically feeling the influence of each other, and they're nonlinear for the reason that there is the Hartree potential and the exchange correlation potential. So this is one of those equations. This is the molecular orbital. Here is the potential that depends on the density. More explicitly, the potential depends on the density through the Hartree term here, what's made of the ionic term, but also the Hartree term here, and the exchange correlation function, which can depend on the density and for GGA function also on the gradient of the density. The density is computed by summing the squares of the amplitudes of the wave functions for all occupied states. And finally, and I'll come back a number of times to that last line, we have to keep all these molecular orbitals orthogonal. So that's basically expressing the Pauli exclusion principle that we can't put two electrons in the same state, meaning when we now occupy these molecular orbitals with electrons, we have to have them separate or orthogonal. So we have to enforce this condition here, that these scalar products of these functions here have to be 0 unless I equals j. So what kind of algorithms are used now when we implement that? The Kohn-Sham equations themselves, we can see them as differential equations, but we can also rephrase that as an optimization problem. Basically, you look at them as the solutions of an Euler-Lagrange problem, which minimizes the functional being the density functional expressing the energy. So in most cases, we actually look at that as an optimization problem. We state the problem as find the wave functions such that the energy is minimum. But it's equivalent to the partial differential equation problem. It's just a different way of phrasing it. The calculation of the Hartree potential here is probably seen in previous lectures, also involves solving a Poisson equation. So knowing the charge density, you want to know what this integral is. And that means you have to solve a Poisson equation, and that's done in the codes such as quantum espresso or CPMD or Q-box. That's done using three-dimensional Fourier transforms, since we're expressing everything in plane waves. Now, computing the charge density itself is also involving three-dimensional Fourier transform, since we start from wave functions, which are expressed as Fourier coefficients. And we need to compute the square of the wave functions in real space. So we have this problem going from reciprocal space with Fourier coefficients to real space and back. So this is another place where we're going to need three-dimensional Fourier transforms. Now finally, this part here, to impose the orthogonality constraints, that can be mapped onto a problem of linear algebra. You can express these products here in terms of matrices. They end up being large matrices. If you want to compute the quantities needed to enforce this condition, you end up multiplying large matrices with each other. So that's just a dense, large linear algebra. So overall, the computational cost of all this process is basically dominated by this part here. This is a term that will scale like the number of electrons cubed. Okay, so if you want to double the size of your molecule, you need 8 times the computer time. Now there are also other parts that scale differently. So the total cost of the calculation is not just n cubed, it's a polynomial in n. So there are some n squared terms. There are some Fourier transforms that cost n log n. So there's a number of contributions, but the bigger one, the largest one, is n cubed, comes from this orthogonality constraint. So we're working in plane waves with the codes that we're discussing. So this is the way we represent the solutions. You've probably seen that also in previous lectures. So just to remind you of the notation I want to use here. So the electronic orbital here, and I will ignore spin for all this discussion. We know we can put 2 electrons in one state, but just for simplicity of the explanation, I will just consider we have spinless fermions, and we can put only 1 electron per state, so it simplifies the presentation. So one molecular orbital here is expressed as a Fourier series. So we have Fourier coefficients, CQJ, and Q here is a reciprocal lattice vector. And the basis set is defined by selecting only those reciprocal lattice vectors that are smaller, if you square them, are smaller than the energy coupling. So this defines a finite set of Qs, and then we have the plane wave expansion. So we have a set of such coefficients for every molecular orbital, for every solution. So if you want, you can actually represent the whole solution of the problem, the solution of the Kohn-Sham equations in the plane wave basis. You can represent that by a matrix. You just pack all these coefficients here, all these Fourier coefficients, in one large matrix. So the column of a matrix represents one solution, one function phi. So and the elements in the column are the coefficients for all the plane waves. And you have many columns corresponding to all the electrons. So I will call this matrix Y here, with this correspondence between elements of Y and the Fourier coefficients of the wave functions. So we're interested in treating large problems, and for instance, we would like to be able to deal with systems that have maybe 10,000 electrons, so that would be 10,000 columns in this matrix, and each column would have a size of 1 million. So that would be a pretty large problem, but that's really what we're trying to do. So it's a large matrix. This is not the kind of matrix you can easily store on a single node of a computer, so that's why we will end up talking about parallelisation. Now notice one thing is that typically this matrix has a kind of a fixed aspect ratio. By that I mean that the width and the ratio of the width to the height of the matrix is basically constant, and that basically has to do with the fact that you need a fixed number of plane waves per atom in the calculation. Okay. In some cases it could be about 100. So you have, think of this matrix here as a very thin, tall matrix. So if we try now to express the various quantities we talk about in terms of that matrix of coefficients, well, the first thing we know is that the energy in density functional theory is going to be invariant if I transform that matrix with unitary transformations. What that means is the following here. Since the energy associated with a solution here is expressed as the trace of this operator here, that's the Hamiltonian, and this is multiplied on either side by the matrix of coefficients, plus a function of the density. And the density in turn is the sum of these values squared. The consequence is that if I multiply this matrix Y by a unitary matrix, it doesn't change the energy. Okay. So it doesn't change this term, because if I make a unitary transformation among the wave functions, the charge density doesn't change. Therefore, this last term is unchanged. And it doesn't change this term. And you can see that because by permuting the matrices in the trace, you find that you can actually eliminate this operator Q by rotating around these matrices here, and you make it disappear. So this is the invariance of the trace under permutation that tells you this energy functional doesn't change under these transformations. So that's something that is actually very useful. It's sometimes annoying, but sometimes it's actually useful, in particular when you want to compute things like maximally localized one-year functions. That's one situation that you will hear about on Friday, where you actually use this invariance to your advantage to try to compute a representation of the wave functions that is the same, that represents the same system, therefore has the same energy, but in terms of localized wave function instead of extended ones. So, in that language, what do we have to do to compute the electronic structure to solve this problem? Well, what it is really is an invariant subspace computation. What it means is that we're trying to find such a matrix of coefficients here that satisfies this equation here. Now, this is kind of an equation that looks like Schrödinger equation. It's pretty close to that. Hy would be equal to eigenvalues times y. Well, here it's a little bit different. The Hamiltonian applied to this matrix is y times lambda, where this is a matrix 2. And if this matrix is diagonal, then this is just a Schrödinger equation. But the difference that we try to use here is that if we let this matrix be non-diagonal, we also describe the same system. So we could have columns of this matrix Y which are not eigenfunctions of the Hamiltonian. We would still describe the same system because we have this freedom of doing unitary transformation among them. So in that sense, this is a little bit less difficult than an eigenvalue problem. It's an invariant subspace problem. And in some numerical algorithms, we can actually use that to just make things a little bit more efficient. So it's, in principle, less difficult to find invariant subspaces than eigenvalues and eigenvectors. So here are the dimension of these matrices. So that would be the number of basis functions would be m. So the Hamiltonian would be an m by m matrix. We never really compute this matrix. We never really compute the elements of H. We just apply H to a function. So this is just basically to express what the problem is, but in practice we will not compute the matrix H and store its elements. This is the matrix of coefficients that we talked about, and this is this matrix which is not necessarily diagonal, but is just a n by n matrix. So n here is the number of electrons in the problem, or number of orbitals. So the way we solve this problem here, now there are several different algorithms to solve this problem, but they're all going to be using the fact that this matrix H is sparse. Now, what does it mean that H is sparse? You know from whatever course you had in linear algebra or numerical analysis that a sparse matrix has most of its elements 0. And that's one definition of sparse. And if a matrix has mostly 0 elements, usually you can show that it's easy to apply this matrix to a vector, to multiply this matrix by a vector. But what we have here is a matrix which actually doesn't have that many 0 elements. They're mostly non-zero. But the Hamiltonian in the plane wave basis can easily be applied to a vector using Fourier transforms. So it's something you've seen most likely in the first lectures of this school, that if you want to apply the Hamiltonian to a wave function, you will apply the Laplacian operator in Fourier space, and you will apply the potential operator in real space. And both of these operations cost of order n, which is the number of basis functions. Therefore, you have a way of computing H times a vector that is cheap. So that's another definition of sparse. It doesn't really mean that the matrix, if you were to compute it, would have 0 elements mostly. But it means it's easy to apply this matrix on a vector, to multiply this matrix by a vector. So this is the property that is used in most of the algorithms that we implement in electronic structured plane waves, at least, that makes it possible to solve these problems with even pretty large basis sets. So I'll just discuss two algorithms that are fairly common to solve this problem. There are many more actually, and this is not an exhaustive review of all the possible electronic structure algorithms. Let me just discuss one here and another one in the next slide. This is what's called a preconditioned steepest descent algorithm. What it does here is that it takes the current set of Fourier coefficients that you have packed in this matrix Y here, and you're going to apply a correction to that to make it closer to the solution for the Conchamp equation. Now look at this term here. We're going to apply the Hamiltonian on this set of coefficients. And remember, so we said we have a way of doing that efficiently by doing Fourier transform whenever we need them, applying different parts of the operator in Fourier space or in real space. So we can compute that. And that costs us order m, n log m operations. So it's a reasonable cost. What this does here is basically to project that correction out of the subspace that's already spanned by the current solutions. So try to think of it as a correction that here would contain some elements that are already in the solution you already have, and some components that are orthogonal to that solution. You're only interested in the part that's orthogonal. The one that projects on what you already have doesn't change anything. So what you want is to project this correction out of the subspace that's already spanned by your solution. This is what it does here. Then there is this operator K, and that's called a preconditioner. So the role of the preconditioner is to accelerate the convergence of the iteration. Basically what happens is if you apply just the Hamiltonian to a wave function, it's going to be dominated by the very rapidly oscillating part of the Laplacian. Right? If you apply the Laplacian operator to a wave function, and any small oscillation that has high frequency is going to dominate the correction. It's going to dominate H psi. Just because if you look at it in the Fourier space, the G vectors, the reciprocal lattice vectors corresponding to these rapidly varying oscillations, appear as G squared in the Laplacian. So this is going to be a large term. Now, if you just use that as it is, the convergence of this iteration is going to be very slow. So what you want to do instead, you want to damp out these rapid oscillations and give more weight to the lower frequency oscillations. And that's what this preconditioner does. It sort of rescales the different parts of the spectrum. It rescales the different wavelengths, the different corrections in different wavelength regimes. So this is an operator which usually is just a diagonal matrix in reciprocal space. Finally, there's just a coefficient here, which is how much of the correction are we going to apply to our solution. And then just apply that correction and get a new set of Fourier coefficients. Now what's going to happen in general is that after you made that correction, these coefficients do not describe orthogonal functions anymore. Right? You started with orthogonal functions, you make that correction, and that's going to mix up a lot of terms and add some terms arbitrarily. The resulting wave functions are not orthogonal anymore. So what we have to do next is enforce the orthogonality again. So now we have to actually apply some orthogonalization algorithm. One of them is Gram-Schmidt. If you remember from a linear algebra course what Gram-Schmidt is, any reminiscence there? You pick a vector, normalize it, pick the next vector, orthogonalize it to the first one, pick a third, and keep on doing that until you have an orthogonal set. So that's one way of finding an iterative solution of the problem of the Conchamp equations. Okay, this is a slightly more advanced way, which is implemented in most recent electronic structure code, called preconditioned DIIS. This bizarre name here was actually given by Peter Poulet, called direct inversion of iterative subspace. No one asked me to really explain why it's called this way. It's a little bit cryptic, but basically what it does is try to make this correction that we talked about in the previous slide, but make sure we apply the right amount of that correction. Remember there was this parameter beta there, that was a number that we just pull out of a hat and try, see that it's not too large. Now this is actually going to do something more optimal in the sense that it's going to give you the best amount of correction that you need to get the optimal correction in that particular direction. So first of all, what it does is it computes a descent direction. So this is the same as we had in the previous slide. It's a preconditioned descent direction of the energy functional. And then, instead of having just an arbitrary coefficient beta here, we keep that direction, and now we try to find what is the minimum of energy along that direction. Okay. This is what is contained in those equations here. And it involves mixing the current solution that you have with the previous solution. So basically, you're going to extrapolate along a direction in that space of matrices and find the exact point where you minimize the energy. So I'm not going to describe that in full detail. In the end, basically, you will make a correction that has this parameter here that can be computed, and then you will start choosing the next direction and keep going. Yes?
This putting down this high frequency and taking care of in the low frequency to make the spectrum more or less uniform. And to do that, this correction which you are talking about, is this correction is just mathematical at this stage, or the choice would depend on the internal time and energy scale of the system? Because finally where we have to correlate with the physical system. Is the choice depend on, you have to make a very intuitive sort of...
Well, it's a good question, yes. So you're talking about the choice of the preconditioner K here. How do we actually define it? It does depend on the size of your problem, for instance. It does depend on your plane wave energy cutoff. So it depends also on the properties of your system. If it's metallic or insulating, it will actually affect the choice of that. So there are usually parameters that we use to define that preconditioner. In the code that we used yesterday, then there's this cut prec value, which was this other cutoff, the preconditioning cutoff, that actually is used to define the precondition. And that choice depends on the size of the problem, on the system, so yes, it depends on the physics. After you've made that choice, it's just a mathematical tool in the sense that once you get to the solution, then you can find that you're going to get the same solution independent of K. Right? So it's just a way of accelerating the process of getting to the solution, but the preconditioner doesn't change the end solution. Okay. So this method, you will find that an acronym in some simulation codes. There's just a choice of an algorithm to minimize.
What do you mean by with fixed potential? You mean the ions are fixed?
Okay, let me explain the title here. I forgot to do that. That's a good point. I'm considering here just the problem of a fixed potential in the sense that there's no self-consistency. Okay, the charge density and the fact that the potential depends on the charge density is not considered here. I'm just going to consider a Schrödinger equation with a given potential. Okay, so these techniques can be used just for any given potential, but you don't have any self-consistency cycle yet. All right, so and then at the end, when you've done these updates here at each cycle, you also have to orthogonalize. So all these algorithms always have this step here. They make a correction that makes you lose the orthogonality of the wave functions, and then you have to recover. You have to get this orthogonality back, and that means there's this third step. Okay, so now is the next step. Right now we're going to include the fact that the solutions will affect the charge density, will affect the potential, and so on and so forth. So we have this dependence of the Hamiltonian on the charge density, which is a nonlinear dependence. So our algorithm now becomes not just an invariant subspace computation, but on top of that there's a fixed point iteration. So we have to repeat that loop here, compute the charge density, or start with a guess of the charge density, then solve this problem for that particular density, and then replace that density again and keep on going until it's self-consistent. And by that we mean when the density doesn't change anymore, that's self-consistent. And there are some clever ways of accelerating this by computing the density as a mixture of the previous steps. So you can sometimes accelerate that, and that's known under the name of Broyden scheme or Anderson acceleration. Those are all kind of equivalent methods. So that accelerates the self-consistency cycles. Now on top of that, now we want to do molecular dynamics. So we have yet another loop around all this. At each time step, we're going to have to redo it all over again. So this means now the time dependence of the Hamiltonian comes from just the fact that the ions are moving. Okay? And at each time step, we're going to have to do the loop that we had before. Okay? So compute the charge, solve the problem for a fixed potential, repeat until the charge is self-consistent. And now once we have a self-consistent solution, compute the forces that act on the nuclei and move the atoms. That's where we're going to have to use the Parallelization algorithm, and then start over again for the next time step. This is basically our 3-loop structure of the Born-Oppenheimer molecular dynamics problem. Okay, so this is just summarizing what I just said. This is the recipe. Go through these 3 steps and repeat a large number of times. So we better have efficient algorithms because we want to repeat that outer loop a lot of times. So ends up being always more than 1,000 times, several thousand times. Just remind you here of the time units that are at play here. 1 atomic unit of time, which is a unit of time that basically you can derive from in the semi-classical view of a hydrogen atom. That would be the time it takes for an electron to go around a hydrogen atom or something like that. So this is a fraction of a femtosecond. Okay, so here we are talking about these kind of time steps. Now in practice, we choose time steps which are in that range here, between say 3 and 50 for heavier atoms, and we'll discuss that a little bit more detailed why you can choose these. So we're talking about fraction of a femtosecond to up to maybe a femtosecond. Right, so if you choose a time step of 4, which is a tenth of a femtosecond, you want to simulate for 1 picosecond, you're going to have to do 10,000 steps of molecular dynamics. And each one of these steps, you're going to have to solve a self-consistent Cohen problem. So how do you choose this time step? Well, in general, as you've seen in the lecture on classical molecular dynamics, if you choose a small time step, the simulation will be more accurate. Remember that in the Parallelization algorithm, you have these errors which were of order t to the delta t to the 4th power. And so if you make delta t smaller, the error is going to decrease fast, so it's better. You can have a more accurate simulation for small time steps. And if you, on the other hand, you go, and if you do that, obviously, then to simulate the same amount of real time, you will have to do more steps. So this is getting more and more expensive. So you have a compromise between accuracy and cost already. Make it large now. You try to go in the limit of larger time steps. You will have larger errors in the integration of the equation of motion. So you have larger errors in the Parallelization algorithm. The limit that is kind of convenient to use is this ratio of 40 steps to integrate 1 oscillation of atomic motion. So suppose you consider a vibration of a bond, you will have a certain amount of time it takes to do 1 period. You should go somewhere like 1/40th of that period with your time step. So what are the fastest oscillations you have in the molecular dynamics simulations? Well, in practice, often it comes from hydrogen. To have a fast oscillation, you need a very strong bond, and a light particle. So that happens. I mean, the worst case really is a hydrogen dimer. You have two light particles and a pretty strong bond, and that's the highest frequency you can get. Unless you want to simulate hydrogen, that's not very common, but it does happen. But in many other situations, you're going to be limited by a bond between a hydrogen and a heavier atom, and that's a few examples that you will find in most organic problems. So a CH bond has a frequency of about 3,000 wave numbers, and that corresponds to a period of oscillation of about 460 atomic units of time. And likewise, you have slightly different numbers here because the mass is different here. Also, the strength of the bond is different. So altogether, you have these kind of periods of oscillation for these bonds. Those are pretty much the fastest motions you have in the simulation. So for instance, if you wanted to simulate water, then you would have, by this rule, if you look at the OH bond being about 400 atomic units for a period, you divide that by 40, and you end up with about 10 atomic units for the time step. So remember, if you want to do 1 picosecond, then that's 40,000 atomic units. So if you want to do a picosecond of water, it's going to be 4,000 steps at that time.
Does it mean for like biological system, DNA and protein, where you have a lot of hydrogen bond and so on, this should be a very expensive?
It does, yeah. It does mean that. And
it may so happen some of the information also would be lost, might not be picked up until you set up a very, very large scale massive simulation. Because there are some very faster time scale involved than this time scale, or maybe some slower time scale involved than this time scale.
Well, if you want to capture the slower time scales, yeah, you're going to need a very long simulation. And because you're limited by this motion, it's going to be extremely expensive. So basically, one way of avoiding that is the constraint that we discussed yesterday. You sort of freeze these motions because you say, well, I don't really care about the fact that the hydrogen atom goes back and from the carbon all the time. I know that. That's not the physics I'm interested in. So I can freeze that, and therefore I can then switch to a faster time step, a larger time step. Get access to other kinds of physics that I'm more interested in. Okay, so having said all that means that if I want to perform Born-Oppenheimer MD for any interesting time scale, I'm going to focus a lot on efficiency of the calculation. And I'm going to have to try to minimize the cost of the electronic structure calculation while minimizing the cost of always a good idea. And what's the simplest approach you can think of? Well, you've done all this work to find the solutions for a given ionic configuration. Now you've moved the atoms a little bit. You're going to start over again to compute the wave functions again. Sounds like a good idea to start from the previous solution, so that would be the simplest approach. You copy the wave functions you had before you move the nuclei, and you start from that. And since we're using iterative methods to solve the Kohn-Sham equations, that makes sense. We can start with a good guess. So that works. But in fact, it's actually even better if you try to use the information about how the wave functions changed in the past. So you try to predict that change and get an even better guess of your wave functions at the next step. So you want to do a wave function extrapolation. You want to start from the previous wave functions you had at the previous time steps and try to say, okay, what is it going to be at the next time step? And use then that guess to start your solution of Kohn-Sham equations. So extrapolation is something that's pretty simple when you have a scalar quantity. Right? You have a function of one variable, you know it at a few points, and you want to extrapolate it to the next point. What do? You're going to take some previous points, some kind of Taylor series, and then you can extrapolate and predict what it should be, assuming that the function is smooth enough. Now, we're dealing with wave functions here, which are assembled in this matrix that is an orthogonal matrix. So it's representing a subspace of our Hilbert space. So it's a little bit more complicated here. It's not a scalar quantity. It's a subspace at every time. Okay? And you want to predict what this subspace will be in a future time. Okay, so as we discussed before, we represent that subspace by this orthogonal matrix Y, and the columns of the matrix are spanning that subspace, which that represents our solution. But we have this problem that this representation is not unique. As we discussed before, we have these unitary transformation Q that can change the matrix Y, but it doesn't change the subspace. It still represents the same problem, the same solution. So how do we do that then? We have a non-unique representation of every subspace, and we try to do extrapolation. So that's a bit of a problem. So imagine here we have computed in an MD simulation, we have computed that subspace in the form of that matrix at different times, and I'm now indexing the time with the index k, and here is schematically is the representation of your solution at the previous time step, at your current time step. What we like to do is get a good guess of what it's going to be at the future time step. Well, you can try something like a straightforward linear extrapolation. Okay, so this is, by the way, the same thing that happens in a Verlet algorithm. Remember, we have the 2 times the current value minus the previous values. So this is the first part of what happens in the Verlet algorithm, and then it's corrected with a force. Okay. So this is pretty much the same idea here. Let's try to guess here this matrix Y tilde by making a linear extrapolation of the previous ones that we had. Okay. But the problem is now, well, these 2 matrices can be affected by arbitrary rotations of these unitary operators. So this extrapolation is actually not well defined. So that brings us the problem of what we call subspace alignment. Since when we solve the Kohn-Sham problem at each time step, we end up with a solution that has an arbitrary phase, or if you want, an arbitrary unitary rotation that mixes the columns of the matrix Y. So there's no guarantee that this matrix will look similar to the one at the previous time step. They are just uncorrelated here. So we can do this extrapolation, but in practice we have to first basically align these matrices, if you wish. So we try to find what is the closest matrix Y k minus 1q. So we look for a transformation Q that will bring this difference to a minimum. Okay. So this is known as the orthogonal Prochrystis problem in linear algebra. This is something that's been studied by a lot of people. It's a well-known problem. So assuming you can solve this problem, find Q such that these 2 matrices are closest, as close as possible to each other. Then you can subtract these matrices in this way and get a good extrapolation. Because that's the best way we have found to guess the next solution during molecular dynamics. Yes.
So is the Y tilde going to be orthogonal matrix?
That's a good point. No, in general it's not. Okay. So if you subtract 2 solutions like that, again you find something which looks close to the subspace, but it's not orthogonal. So you have to apply again an orthogonalization before you continue. Okay, so at this point, let me switch to the second part of the talk. So that was just so far. Yes.
So I just had a question on this part, and it's that so what you're interested in is the density, and here you're choosing to work in the space of wave functions.
So in other words, you're asking why don't we extrapolate the density?
Yeah.
When you solve it, yeah, I mean that's a good point, and that is helpful. But then you really have to solve for all the wave functions again, right? Because to actually compute the solutions of the Kohn-Sham equation at the next step, you will have to refine the wave functions again. So It helps if you start from the good potential, which you get by extrapolation of the charge density. That's true. But you also would like to start with a good wave function. So it's not enough to just extrapolate the density. And that's why we go through this. So a number of things in the energy functional depend on the wave function. It's true that in principle the functional is just a density functional, but in the Kohn-Sham scheme, the kinetic energy depends on the wave functions exclusively, and the non-local potentials also depend exclusively on the wave function, so we still have to do it.
What does this F mean?
Oh, yeah, this is denoting the kind of norm that we're using to measure that difference. And this refers to the Frobenius norm in linear algebra. That's a complicated name to just say it's the sum of squares of all the elements of the matrix. So since we're subtracting matrices here, we have to specify a little bit how we measure distance between matrices. Typically in a vector space, we just have vectors. There's a natural Euclidean norm. If you measure distances between matrices, also sometimes you use the Euclidean norm. In this case, it's just the sum of squares of coefficients of the matrix. All right, so these were just sort of examples of the kind of difficulties you encounter when you want to implement first principles MD for the electronic structure problem. And that's all in the context of the Born-Oppenheimer approach. So we still want to compute the ground state of the electronic problem at every time step. Okay. We are close to the 45 minutes, or aren't we? It could be a good time, since we changed subject, to take a 5-minute break, and then we'll continue. Let's say we continue at 10. How about that?